Hi, welcome to another lecture on Calculus 2. Today's topic is about arc length. So the idea is that we have a curve in the plane and you want to find out how long it is. So a typical situation is that the curve is given, y is equal to f of x, a beginning and end are also given, and we want to find out how long the curve is starting from this point and all the way to the other one. We are going to explain and give some examples for the following formula. Length turns out to be the integral from beginning to end of square root of 1 plus the derivative of this function squared in square root integrated from a to b. Now let's go ahead and see where does this formula come from. You have learned in calculus that we always try to solve the simplest case, and then out of that we construct the more general case. Well, what would be the simplest case? Simplest case would be, of course, if you have a straight line. If you have a line that goes between 2 points, and then you want to find out how long a certain segment of it is. Well, that problem is very simple. You have done this thing back in pre-calculus or college algebra. You find out the run, find out the rise. So this is the run and this is the rise. Typically you have some notation for these things like delta x, this one delta y. Well, the length that you want to calculate is the hypotenuse of a right triangle whose legs are delta x and delta y. Typically this one is shown by delta s or whatever you wish. So delta s, the hypotenuse by Pythagorean theorem, is delta x squared plus delta y squared. You calculate rise and run and square them, add them up, and the length will be, well, square root of this thing, delta x squared plus delta y squared. Well, step by step, let's see how can we get that one. If I go ahead and calculate factor delta x squared from inside this radical, if I go ahead, take delta x squared, it doesn't look like it's factorable, but let's push it. So I factor it. That means I have to divide these to delta x squared, and of course delta x squared comes out. Let's suppose for a moment that delta x positive, so when it comes out it's just delta x, and the radical, well, delta x divided by delta x is just 1, and delta y over delta x, we can divide them first and then square it. Do you see the similarity between this and that? So instead of dx, I have a delta x. Instead of this derivative, I have delta y over delta x, which is the approximation of the same. I have the same square root and the 1, they are all the same. Well, what does it mean to integrate from a to b? Well, the idea is very simple. If I have a curve instead of a straight line, draw a curve like this, and suppose this is the beginning point and this is the ending point. Well, what would I do? I can go approximate this by bunch of straight line segments. So for example, I can go all the way here into the middle and then go there. If I want a more precise approximation, perhaps I make a journey with lots of smaller pieces. So I can, for example, divide this into 4 pieces and go from beginning to end. And what would I do? I calculate a delta s for each of them. So the very first piece, perhaps delta s1 and delta s2 and delta s3 and delta s4. So the length would be of course the sum of all of these things. so if I want to get exact length, what would I do? I just make these segments smaller and smaller so that they all tend toward almost zero, and then there will be infinitely many of them, and then this L that I'm approximating here instead at the limit becomes, so we are adding up things of this type. That addition that we are doing, that addition is done by integration, and then I have the function I'm integrating is 1 plus delta y over delta x. That's same as the derivative dy dx. I have to square that, and instead of delta x you write dx. The act of summation that you're doing here is a definite integral from the beginning to the end. So that is the idea behind the formula that we have. Now there's several things to do. One is some practice problems to see how we actually carry it out. And then there are some other issues. Sometimes your functions are given as x in terms of y. That is, the role of x and y are interchanged. So there's going to be a similar formula in that case. And later on we might have a similar topic in other coordinate systems and parameterized curves and so on. But let's go ahead and start by some examples. I want to mention that in your textbook you can find some examples. The first one of them is perhaps y is equal to x to power of 3/2, I believe. So that is the first example. You can read in the textbook and see that how you would carry this out. And then you have another example, x equal to y squared or y equal to x squared. This is of course your parabola. You will see that the integration problem there becomes somewhat complicated, as it's quite common in these problems that because of this square root we have to do some extra work if we ever actually can finish this. Then another example in the text is for a peculiar looking function y is equal to x squared minus 1/8 of logarithm of x. These are not the kind of functions you would have seen previously in any of the exercises that you have done. These are kind of created so that this integration problem becomes doable. So these are specially designed problem so that we actually can finish the problem. In general, for example, if you take y equal to x cubed, you will notice that are the methods that we know or are there. They're not going to tell us how to actually calculate the integral. So expect a bit of integration challenge. Typically, if you just pick a random function and try to integrate this formula, you'll see that it's not going to work out. Okay, let me for example start with one problem here. So here's an example 4 from your textbook. Y is equal to x cubed over 3 plus 1 over 4x. So this is the example function, and x is between 1 and 2. Just to get an idea of what we are dealing with. It doesn't change it, but just to see how. So I just want to take a look at this thing before we actually dive into the integration problem. What curve is it? To do this thing quickly, of course we go to Desmos. Y is equal to, what was it, x cubed divided by 3. Oh no. And then plus 1 over 4x. So looks like this, and we want to go from x equal to 1 to 2. So x equal to 1 is here and 2 is over there. We want to find out how long this thing is from here to here. That's the idea. So let's see if we can figure that out. So we go back to our scratch paper. Sorry. So first step is to find the derivative. Derivative, I take a derivative of first one, 3x squared over 3, and derivative of 1 over x is minus 1 over x squared. Simplify x squared minus 1/4 of x squared. Next we need y prime squared, the derivative squared. So I need x squared minus 1 over 4x squared, all things squared. The first item squared, x to the power of 4. Second item squared is 1 over 16x to the 4. Twice the product of the first and the second. Let me write it out so you see. All these problems work on this following nice cancellation. That the x squared cancel, and then you see x4 plus 1/16 x4, and then minus 1/2. As we said, it's 1 plus y prime squared in the expression. So I need 1 plus y prime squared. So it's going to be 1 plus x4 plus 1 over 16 x4, then minus 1/2. 1 and minus 1/2, well, we always get a plus 1/2 in this process. 1 over 16 x4 plus 1/2. Now the question is, what if I do square root of this thing, what happens? Well, notice when there was a negative here, I got a negative. When I have a positive, all that happens is that you will have a positive over there, x squared. So let me write down the expression first. X to the 4, 1 over 16 x4 plus 1/2. Convince yourself that this is x squared plus 1 over 4x squared. Why? Because if I square this one, I get x4. Square of this one is 1 over 16 x4. Twice the first and the second is this plus here. So now the length is going to be the integral. Here is beginning and end of the problem for us. This is going to be from 1 to 2 x squared plus 1 over x squared dx. That's of course now the easy part. So we differentiate this one, x cubed over 3, and then I have 1/4, and the derivative of 1 over x squared is minus 1 over x. Is that right? Minus 1 over x is antiderivative of this. We better know this by heart, and then we have to calculate from 1 to 2. So I'll have 2 cubed and then minus 1 cubed over 3 plus 1/4 of, at the top end I have minus 1/2, at the bottom end I have this one. So I'll have this is 7/3 plus 1/4 of, this is minus half plus 1. So this is 7/3, and this becomes 1/8, and then, well, you just add them up. So this rather peculiar function has a length from 1 to 2, almost 2.5 or something. To go back here, what we are saying is that from this point to this point, uh, the length is almost 2.5. Okay, so that was one example. Let's do another example. This one says 36y squared is equal to see, x squared minus 4. What's that? Cubed, yes. And that is x is from 2 to 3. And it tells us consider y is positive. Again, just to have a ballpark figure of what we are dealing with, let's go ahead and take a look at so let's another function here. I have 36y squared is equal to x squared minus 4 to the power of 3. Okay, so that's a weird looking graph. It says x between 2 and 3. X between 2 and 3 means you start from here. Well, you have these 2 points. So what is the curve that is intended? The problem says let y to be positive. If y is positive, meaning I'm starting from here and going to this point, that is the trajectory we want to travel and find out how long that is. So let's go ahead and do that. Okay, so we have to either find y in terms of x or x in terms of y. Let's go ahead and take a square root here. So say 6y is equal to x squared minus 4 to power of 3/2. So I took the positive root here, and now I can differentiate, or first perhaps find 1/6 of x squared minus 4 to power of 3/2. Y prime factor is 1/6, exponent is 3/2, derivative of the base is 2x, then x squared minus 4 to power of 1 less than this would be 1/2. So I simplify this thing, it becomes x over 2 times x squared minus 4 to power of 1/2. I need to square my y prime, so that's going to be x squared over 4 times square of a square root will be just this expression. When I multiply, I get x4 to 4 minus x2. Is that right? So y prime squared plus 1, I have to add 1 to it, simply x4 over 4 minus x2 plus 1. Now I need to take square root of this. Y prime squared plus 1 is square root of x to power of 4 over 4 minus x2 plus 1, and that is x2 over 2 minus 1 squared. Check that this is same as that, because the first item squared is x4 over 4, 1 squared is just 1, twice the first times the second is that expression. Now this comes out of square root, and our x was larger than 2, so this is larger than 1, and then it's positive, so that's how it comes out. integral from 2 to 3 of this expression will be integral from 2 to 3 of x squared minus 1 dx, and that's going to be x cubed over 6 minus x between 2 and 3. So now 3 cubed minus 2 cubed over 6, and then minus 3 minus 2, and the denominator just 1. So I'll have 27 minus 8, that is 19, 6 minus 1, and that is 13, 6. So the length of the curve, we had it here, I guess, is that right? We said it's going from 2, is that right? 2 to 3. This length, we found it to be 13, 6. And so on. Let's see, maybe we do another exercise where problem 14 maybe. The role of x and y could be exchanged, so let's do one of these. Y to power of 4 over 8 plus 1 over 4 y squared. So if x is given in terms of y, the length formula we use, starting from beginning to end, of square root of 1 plus x prime squared dy now. So that's for a picture that x is given in terms of y, and you have a beginning and end like C and D here, and this is the integral you're calculating. You're calculating the length of that piece. So I need x prime. What do we mean by x prime? We mean dx dy. Well, how do you differentiate? Just as usual, this becomes y3 over 2, and this becomes minus 1/2 of y3. Is that right? Because y to power of minus 2, I factor minus 2, it simplifies with a 4, I get minus 1/2, and the exponent becomes 3. Now x prime squared is going to be y3 over 2 minus 1/2 y3 squared. It's going to be y6 over 4 and 1 over 4 y6, and then when I multiply these two together, twice the first times the second, so twice y3 over 2 times minus 1 over 2 y3. So that is y6 over 4, so 1 over 4 y6, and these always becomes a minus half. Then, meaning if it didn't, our integral wouldn't be easy. X prime squared plus 1, if I add 1 to this, this minus 1/2 becomes plus 1/2, y6 over 4, 1 4 y6 plus 1/2. Square root of this is now easy. It's just the original expression with the plus y cubed over 2 plus 1 over 2 y cubed. So the integral, I forgot to write from where to where, the y between 1 and 2. In this problem, so integral from 1 to 2 of this expression, 1 plus x primes dx, that is integral from 1 to 2 of y cubed over 2 plus 1 over 2 y cubed dy, becomes y to power of 4 over 8, and this is y to power of minus 3 becomes y to power of minus 2 over so integrating from 1 to 2, we just put our numbers there. 2 to power of 4 minus 1 to power of 4 over 8 minus 1/4 of 1 over 2 to power of 2 minus 1 over 1 to power of 2. First piece is 16 minus 1 is 15, 8 minus, and this is minus 1/4 of that's 1/4 minus 1, so 15, 8 minus this is minus 3/4, this is 3/16, if I'm not mistaken, 16, 30, and so that's the length of this one. Okay, sometimes you might be asked, we said previously, sometimes we do not succeed in calculating the integral. Here's an example. What's the length of this curve from 0 to 2? Well, the length would have been the integral from 0 to 2 of square root of 1, derivative of this 3x squared, and then you square that, becomes 9x4 dx. Well, what is this? We can think and think and think, and I cannot produce an integral for this. I cannot find the antiderivative of that expression. It doesn't fit in any of the functions we already have developed. So what's the option? The option is to say, well, that's our answer, or to use numerical integration we learned last time in the previous lectures. We can approximate this by dividing it from 0 to 2 to n intervals, and then calculate that approximately. In this case, the textbook says just set it up. You don't need to bother with calculating it. So that is the approach here. Okay, so I guess this will do for our case. So we learned that formula. Let me repeat the two formulas that we have. So we have, if our problem expressed in this traditional case that you have x and a y, L in this case, suppose you have y given f of x, you integrate from a to b of 1 plus f prime of x, I think squared dx. If it was given the other way, like this is x, this is y, and then you have beginning and end. Again, you do the integral, and now suppose x is given as g of y, so you differentiate g prime squared plus 1 square root and dy. Let's also do an example of curve length function. So sometimes we are asked to develop a function that calculates arc length for a variable endpoint. What do we mean by that? Sometimes you have a function in mind and you have a starting point A, but the ending point is some variable point. In that case, you take your axis to be t and say here is your y, and y is some function of t. The length that you find now is going to depend on x. As x becomes bigger, your length becomes bigger, and so on. So in this case, we say we have an arc length function. Arc length function simply means the stopping point of the arc is moving. So from a to x, and then you do the same integration as before, f prime of, let's call it a t, so the letters don't run into each other, and then you find that integral ending point is x, and that becomes an arc length function. Here is an example. It says suppose y is sine inverse of t plus radical 1 minus t squared. Find the arc length function s of x starting at 0.01. Okay, so we need y prime as usual. Y prime, what's derivative of sine inverse? Derivative of sine inverse is 1 over radical 1 minus t squared. What's the derivative of this one? Derivative of interior is minus 2t, exponent is 1/2, and the new exponent, so you write it at 1 minus t squared to power of 1/2. 1/2 comes in front, derivative of minus t squared is minus 2t, and the exponent becomes minus 1/2, which gives you this radical. I simplify the 2's, so I'll have 1 minus t over radical 1 minus t squared. Therefore y prime squared is going to be 1 minus t squared over 1 minus t squared, and I write this 1 minus t times 1 minus t, this one 1 minus t times 1 plus t, so this cancel. 1 plus y prime squared, therefore it's going to be 1 plus 1 minus t over 1 plus t. I add them up, I get 2 over 1 plus t. So the integral from 0, this is the 0, to x of square root of this, what is that going to be? Let's factor this thing. I put a radical 2 outside. 0 to x of 1 plus t to power of minus 1/2 dt, and that is radical 2 1 plus t to power of add 1 to this thing becomes 1/2, divide by that, so it's going to be 2 radical 2 times 1 plus t in radical from 0 to x, and so it's going to be 2 radical 2 radical 1 plus x minus at 0, this is going to be just 1. That is our s of x. S of x became 2 radical 2 times radical 1 plus x minus 1 for x is larger than 0. Okay, we did multiple exercises from this section. I hope you go ahead and do a few on your own. Just look at the problems at the end of the section and just select 10 of them, and that should do it. Okay, until next time, good luck and God bless.